All right, so 5.7, Foundations of Math 10. I believe this is the last section. Foundations of Pre-Calculus, Math 10 by Pearson. This is going to be on page what? 311?
Yeah.
Awesome, 311. And this, I think, is the last section in your chapter, right? Last section of the chapter. Okay. So 5.7 is entitled Interpreting Graphs of Linear Relations. Interpreting Graphs of Linear Relations. So we know about some characteristics of graphs of linear relations, right? We know that a linear relation is a straight line, points in a straight line. Now, technically they can be vertical points, it's a relation, straight line. But if we're talking about functions, which are most useful in math, those lines are slanted somewhat. They aren't straight up and down, they're slanted somewhat, okay? So if it's a straight line function, that's what we're going to encounter most often. So here's a straight line on the screen here. And this is a function because it passes the vertical line test, right? Any vertical line you stroke through that graph only touches the graph once. So it's a linear function. Okay. And notice that this little notation right here, do you remember this? This is function notation. Talked about this. This is writing a relation in two variables there, a function in two variables. So f of t. When you see function notation like this, like f of t with the brackets like that, that means it's a function. Okay, function notation is what that is. All right, so here we're interpreting the graphs. Okay, we're not describing characteristics of the graphs, we're interpreting the graphs. So characteristics, straight line, function, right? There's an x-intercept on the bottom, a y-intercept on the side, stuff like that. So we know about it. We know what the table of values looks like, okay? The consistent jump over here, consistent jump over here. We know what the function looks like. Y equals mx plus b is a pretty standard equation for a... So we know about the characteristics. Interpreting means looking at the graph and trying to find out information from the graph. So we have a title of a graph. We have the dependent quantity over here of height on the left. We have the unit of the dependent quantity of m. That stands for what? Meters. Height in meters. Good. We have the independent variable, which is time, and the unit minutes. And so we're going to be able to look at this graph, the points, the line, and the intercepts, and we're going to try and pull out information about the situation from the graph. Okay? Interpreting graphs of linear functions. Okay, so with this graph, it says in your book here, float planes fly into remote lakes in Canada's northern wilderness areas for ecotourism. This graph shows the height of a float plane above a lake as the plane descends to land. Okay, so the first question here is, where does the graph intersect the vertical axis? At what point does the graph intersect the vertical, straight up and down axis?
1,000 meters.
Okay, so 1,000 meters in height, right here. That point is 0, 1,000. Okay? What does this point represent? What does this point represent? Touching down. Okay. This point wouldn't represent touching down. Yeah, so, okay, so touching down would be at a height above the lake of 0. So that's on the other end of it. We'll get to that. We'll get that. So you corrected yourself. What did you say?
Start of descent.
Yes, it's the height of the plane at the start of the descent, or at least at time 0. Okay? We don't know if the plane's been descending before this. This is just the time where we start recording the information. So this is the height of the plane at time 0. If the question does say, you know, at the moment the plane begins to land, that's where this starts, then you can say at the start of its descent. But at least at time 0, when we begin measuring this information. Okay, so the height of the plane when we start the timer, right? Start the timer. Okay, awesome. What about the next little bit? Where does the graph intersect the horizontal axis? We talked a little bit about this already. It's way over here, and this point is at 10 what? 10 minutes. Okay. So at 0 minutes, it was 1,000 meters above the lake. After 10 minutes, the height of the plane above the lake surface is 0. So this is where it touches down, okay? The plane landing and then touches the water. Okay. So how long does it take the plane to descend from 1,000 meters to touchdown on the lake? 10 minutes, right? 0 to 10. Okay, so it takes 10 minutes to descend. That seems like a long time, doesn't it? It seems like a long time to me. If it was like a big passenger, plane and you're on your descent, that's like almost 20 minutes, I guess. So a float plane just seems like it's a little lake and it's a littler plane. I would think it would go down further than, quicker than that. But 1,000 meters is fairly high. Okay. Where does the graph intersect the horizontal axis? We talked about that one. What is the rate of change of this graph? And what does it represent? So remember, the rate of change is the slope, right? The slope. Now the slope, we recall, the slope equals the change in y divided by the change in x for any 2 points. For any 2 points. And I don't think I've written this down, but we should know for any 2 points, right, on the graph. Any 2 points on the graph. Any 2 points that you know the values of, okay? The rate of change. Now, it's easy, I think it's pretty easy for us to take this first point that we just saw and this last point that we just talked about. We could use those points. The coordinate here is 0, 1,000 for this first one. The coordinate over here is 10, 0. So with zeros, adding and subtracting, it's going to be pretty easy with zeros, so that's kind of nice. So the slope, I'll do it over here, slope equals change in y, okay, so between this point and the second point, the change in y values is 1,000 and 0. So what's that change? Well, you should do the second point value, 0, minus the first point. When you're taking the change in something, always use the second point first, subtract the first point. Because in this way, you will get the proper sort of sign, whether it's positive or negative. So always do final minus initial, okay? And if you haven't heard that in science yet, you'll hear that in science. Make sure you do final minus initial to determine the change in something, okay? So obviously, the height above the lake has gone down, right? It's going down, so this rate should be negative. So here we have a negative on top. Now, we should go to the same point that we start with, so this point, and I'm going to do 10 minus 0. That's the change in x, 10 minus 0. So I have the slope equals negative 1,000 divided by positive 10. So that's going to be equal to negative 100. And what would the units be? Because the units are pretty important, right? What are the units? The y units are meters, because this is meters up here. And the x units are minutes. Okay, because this is minutes down on the bottom. So negative 100 meters per minute is the rate of change, or the slope of this line. Everybody see that? Okay. Now, just out of curiosity's sake, just real quick, what happens if we didn't pick the intercepts? We picked any other 2 points. Like, let's just say we picked this point. Okay, come on, computer. This point and this point. Could we calculate the rate of change? You bet we could. And it should be the same because it's part of the same line. So I'm going to do this real quick. M is our common, I shouldn't do that. M is the common representation letter for slope, but I'll do slope because M is in meters. I don't want to confuse you. But we're going to do 800, okay, is our y value here. So this is going to be 2, comma, 800, right? And this one's going to be 5, comma, 500? 5, comma, 500. Okay, so the slope is going to be 500 minus 800, that's minus 300, divided by 5 minus 2, that's going to be 3. Oh, wow, negative 100. See that? With any 2 points, you should get the same slope if you did things correctly. Good? Capiche? Understando? Comprende? You got it, man? Okay. Good. So what does that rate of change represent? In your own words, what does this represent? Don't just say negative 100 meters per minute. What does it mean in the context of the problem? Go ahead. Give me a sentence. Yes. The plane descends, goes down 100 meters every minute. Perfect. That's what it means, yeah. Or the plane drops in altitude 100 meters for every minute that it's on its descent. Awesome. Okay, I want to talk to you a little bit about restrictions here. restrictions, when we're talking about word problems, a lot of times within the context of the problem, there are natural restrictions to solutions for a variable. So for example, height above the water in this problem can't be negative. The plane is not plunging beneath the water surface and like, turning into a submarine. This only happens in like Batman movies or something. So it's a float plane, right? So there probably would be a maximum height somewhere up in the atmosphere there where the plane is not going to go any higher than that. We don't know that. But what's natural is that we know that there's no negative numbers for the height above the water. Does that make sense? So the restrictions on the domain, that's the x values, and the range, the y values. Okay? There are natural restrictions, and these values, the restrictions, would be the values that are not acceptable for the question. And an example there was height above the water cannot be negative because the plane is not going to plunge into the water and keep flying. As far as domain goes, okay, the plane is landing, so you could say that the domain could be restricted to 10 minutes. Okay, it can't be more than 10 minutes because that's when it lands. So the graph is going to go down, 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 hit the water, and then the graph's just going to be flat, like forever, until it takes off again. But if we're talking about the descent or the landing of a plane, you could say, hey, my domain is restricted from 0 minutes to 10 minutes. That would be reasonable. Okay? All right. Let's do this example together. And this is in function notation, so this is a function. And this is in mx plus b form, so this is a linear function. So please write this down real quick. We're going to sketch it together. And just to make sure we're all on the same page and we can do this, should be pretty easy. I've done this already before, so this should go quick. All right, so we are sketching this here. We just had a 20-minute lockdown drill, so yeah. Let's see. All right, so why don't we go ahead and sketch this now. So this is a function notation. Remember, this is the same as just y equals. Okay? So that's why I have a table of values x, y. This y could also be f of x. Okay? It's the responding variable. So when we're graphing, remember, what we can do is basically choose arbitrarily, or that means with no real pattern or reason. We can choose any numbers for x, and we can find the corresponding values for y for those numbers. Now, we don't want to pick like negative 1 billion or something, because we want to sketch this. So we want to keep it probably close to 0. We want some negatives and some positives, and maybe a 0 would be good. So I'm going to pick negative 3. I see negative 3 I've placed on here at the far side. So if x is negative 3, I'm going to find out what the corresponding y value is. And so we basically, you guys know about this, right? So you just plug it in there, and that's 6 plus 7 is 13. So 3 is going to be 13 right about here. Okay, so that's 313, that point. And 13's there. No, it would be positive 13. If it's negative 2, negative 3, that's a positive 6 plus 7. It's 13.
Would it be negative 3, 13?
Over here, yes, negative 3 here. Yeah, I got it here, yeah. But you're right, negative 3, 13 is the point there. You got it. Okay, so let's choose negative 1. Let's go negative 1. So this is going to be 2 plus 7 is 9. So we're going to have 9 there. So negative 1 is going to go to 9. And let's do 2 on the other side. So negative 2 times 2 is negative 4. Plus 7 is positive 3. So 2, 3. And let's go 3. So 3 is going to be negative 6 plus 7 is negative 6 plus 7 is positive 1. All right, so if we drew these real carefully, let me just touch this one up, then we would see that this should be a straight line that connects those points. Okay. Now, there's no context for this question, so we could actually draw a straight line between these points and connect them, which I think would be a great thing to do if I could draw a straight line. So if you guys have ruler and graph paper, that would be really good to make sure you have that with you, okay? So you should be drawing lines that are better than my freehand on this tablet here. Okay, so 3 was 1. Okay, so notice this is a negative slope, so the line goes down from left to right. And if we take any 2 points and subtract the y values, so if we did 1 minus 13, and then we did 3 minus negative 3, what do we get? We get 12 over 6. We get 3 plus 3, 1 minus 13, negative 12 over 6, which is negative 2 as a slope. And that's what we see here. Okay? All right. Let me ask you a few questions about this graph right here. It's in your textbook. But here's my question. Okay, since we're interpreting graphs now, what could be the title of this graph, or what could be the situation described in this graph? Okay, now be specific. Don't just say distance versus time. Okay, I see. It's distance and time. But what could be the title of this graph? So what's the situation here? What do you think it could be? Sorry? Throwing a paper airplane? Okay. And so the distance is what? Is away from what? Or above the ground?
Yeah.
Okay. So, okay, so the height of a paper airplane over time, you're throwing it from, notice this right here, this is 6 something. So if it's feet, you could throw it from 6 feet like this. Okay, most of you are under 6 feet, so you throw it just above your head. Okay. Now, I suppose this is a steadily increasing height. So that paper airplane would go in a straight line, and it would be ever increasing until this time at least here. So this would be about 14 something. So if this was seconds and this was feet, we could throw an airplane and this airplane would just constantly rise until at least this time, 14 seconds. Okay, well, that's fairly reasonable. Yeah, that's a good idea. Anything else? What else could this be?
Going to work.
Going to work.
Oh, like up a hill.
Going to work.
What?
Wait, how do you go to
It could be
work?
like with that helicopter from your flying.
Oh.
It starts like on top of
Yeah, yeah,
the
yeah, wait,
distance
no, I
away.
Okay, there's another one here. A helicopter is taking off and starting at on the top of a platform or something, building. Now this could be 6 what?
6-story building.
6, okay.
Like 6 stories.
Well, distance would have to have some kind of distance measurement. If you said stories is not like an actual measurement, you know what I mean? Stories would have a certain number of meters per story or feet per story. So distance in meters, maybe, if you had a 6-meter platform, 6 meters off the ground, that's about half the height of the school here. So if you had a platform that high, it could start at 6 meters, and then it would take off. Now the direction, as long as it's just above the platform, right, it would be taking off fairly steadily, obviously very steadily at a rate of change. For the next, I mean, if this was seconds, right, for 12 seconds, it would be taking off slowly at a steady rate and reach about 13 meters or so after about 14 seconds. So that's reasonable. Yeah, that's good. Now, traveling to work, the thing is about the traveling to work idea is, where are you starting from? You're starting 6 meters away from something, or 6 miles away, or 6 kilometers away from something.
Driveway.
So what is this from your driveway?
No, like that. 0 is your.
You have a long.
You have 2 buses to take, and that's from the second bus.
What?
That's
No,
not
like
from the-
0.
Okay, so you-
How far you are from your bed? 0 is your house, and 6 meters is away is your driveway.
So 6 meters from your
6 meters
from your
from
house,
bed. Yeah.
from your bed is your driveway. So you get in your driveway, and
your front door.
the front door. Okay. All right. Well, if this was, so would this be minutes then? Would this be minutes or
Yes.
minutes maybe going to work or school? Okay. So you're 6, and this is meters.
This is
So you go like 7 meters in
No,
14 minutes.
It
takes you 12
it's
minutes to
actually,
get 12 meters in your house.
It's
The
actually
first distance
seconds.
is in kilometers, and the second
So you go
one-
7 meters in this many
No,
seconds.
it's in days.
Yeah, in like.
Okay,
four-
this maybe
you
this
go-
is seconds?
You go 7 meters
That's,
in
it's
4
in
seconds.
days.
I think it's milliseconds.
No, it's in days.
Yeah, I think it's in
Days. You're doing an army crawl to work. Okay, from the edge of your driveway. Okay. All right. Okay, I get the picture.
Not leaving from work.
Okay. Here's another graph for us to take a look at. So this is cost versus number of yearbooks, okay? So number of yearbooks that are purchased, okay, as that grows, the cost obviously grows. So let's see. If 0 yearbooks are purchased,
All grade 9 girls, please meet in Ms. Clark's room for
$500
devotions. And all
bucks.
grade 10 boys, please meet in Mr. Sorstad's room for devotions.
okay.
Again, grade 9 girls, go to Ms.
So before any yearbooks are ordered, it's $500 for the printing fees or whatever, okay? So that's your flat rate, $500. So then 50, okay, now the total cost is $1,500. So what is the rise between this point and this point? 500 to about 1,500 looks like, is $1,000. $1,000 per how many yearbooks? 50. Okay, so what is that? It's going to divide by 10. 100 divided by 5 is 20. So $20 per yearbook.
Is that a
Okay.
scam?
That's pretty cheap. It's really cheap.
Yeah,
Um,
it's a scam.
So does it make sense to, should we connect these points?
Yeah?
Yes.
Yes, yes.
No.
Well, maybe because
Mm,
it's like a
No,
school
no,
and
because you
every
can't have
student
like
get
0.5
one.
a yearbook.
Well,
Okay.
You could like cut the book in half.
Okay. You can't have 0.5 a yearbook. So I like that in the sense that a solid line would have to contain every number in between 0 and 50, even like 13.772.
But like a
So that doesn't really make sense. Okay.
What if you're missing a page? It's not a complete.
Okay, so maybe not connected because you can't have a fraction of a yearbook that you would sell. Okay, would it make sense to put dots every, maybe 10 or something? 1, 2, 3, 4. Then you'd have a jump in price every 10 textbooks.
Yeah.
I don't know. Would that make sense that they would charge the same price? They would charge only $500 and still give you 10 textbooks? So that would be like a little line here and then a little line there, and it would be the same. I don't know. Maybe you could only order groups of 10. You could only order groups of 10, maybe, or maybe you could only order groups of 50.
But
That's what probably I would guess with this. If these points aren't connected,
$500 for 0 yearbooks.
right? That's kind of your printing fee, your flat fee there.
this is the cost of the school, correct? Like how much it costs to print
Yeah.
them, right?
Well, for a number of yearbooks, so a school might be ordering this. Yeah. So because these aren't connected, what you can guess from this, okay, listen up, this is important. What you can probably guess from this or infer from this is that you can only order groups of 50 textbooks, you see? Because no textbooks, printing fee of $500. The next option, the minimum order is 50 textbooks. So this is your minimum price to get any textbook, yearbooks. Then you have to order another group of 50. If you want more than 50, you have to order 50 more. And so that's why these points are separate, because you're right, point something of a yearbook doesn't matter, doesn't count, it doesn't make sense. And groups of 10, let's say, they're not on here, so the company may not be offering that as an option. So yeah, you have to order groups of 50 textbooks, and it's $20 per, I keep saying textbooks, per yearbook. Yep.
So where it says 50, isn't it at 1,500?
Yes,
Yeah.
that's what I said.
Yeah. but
So
on the-
this calculation, but this is not the point. This
Oh,
is the
yeah,
the
yeah.
rise over run to get the slope, right? The slope is the price per yearbook. Yeah, that's right. Now, that's actually a good point. Folks, listen. If you have a line from 0, 0 going somewhere, then you can just take this point and the y divided by the x is the slope, because you're actually subtracting both by 0 and 0. But if this doesn't start at 0, 0, you have to be very careful with that. So that's a good point. Yeah, good point. You can't just take a point and say, oh, the y divided by the x is my slope. It doesn't start at 0, 0 here. Okay. All right, so the bell's going to ring here right away. Just a reminder, there's a Chapter 5 test on Thursday for you guys this year. And this is the last section. So I'll flip over to your assignment. Sorry, I'm not laughing at you. I'm just, well, I'm laughing at you. Sorry.